Today we have to study addition and subtraction of signed numbers, but the negative numbers are represented in 2's complement. So let us see. So let us first take addition. So let us suppose that we have to do an addition of plus 6 and plus 13. We have to add these two things. So plus 6, if I say that we represent numbers by 8 digits, so this 0, this 6 will be this thing, and 13 will be this thing. Then we simply do an addition of them, that 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 0, 0 1, carry 1, and like that. And this number, if we see what is this number, this is 19. So this is plus 19. We can take another case where this is negative and this is positive, and the operation to be performed is addition. So since this is a negative number and we are currently doing representing this negative number in 2's complement, so this minus 6 we will represent in 2's complement. So what is the 2's complement? You will take plus 6 and do a 2's complement on that, including the sign bit, then you will get this thing. So this is minus 6 in 2's complement representation. So for 2's complement, you can take plus 6, then do a 1's complement on that, and add a 1 on that. So this is minus 6, this is plus 13, this thing, and then you just have to do a addition of these two, because the operation we had to perform is addition. So we will do 0 1, this is 1 1 1, and so on, and this comes out to be positive triple 1 means 7. Obviously this will be plus 7. And here obviously when you do this thing, there will be a extra bit that we will discard here, right? That ninth bit, um, we will discard that ninth bit, and this is the answer. This is plus 7. And now third case is plus 6. This first number is positive, second is negative, and this is greater. And this plus 6 is represented by this. Minus 13 will be the 2's complement of plus 13, which is this. Just add them up. This comes out to be this. And if there is a carry, you discard that. And obviously this is negative number. And this answer, since it is a negative number and we are currently dealing with 2's complement numbers, so this answer is in 2's complement, because all our addition and subtraction is going on in terms of 2's complement. We don't need to convert it now. We will keep it like this. We will just say that this answer is in 2's complement. And how will we come to know that this is in 2's complement? Because this one tells us this is a negative number, and currently we are doing the 2's complement representation. Similarly, if we do minus 6 and minus 13, so this is 2's complement representation of minus 6, and this is of minus 13. When do you do an addition, there will be extra bit that will be discarded, and this bit will represent that it is a negative number. That means this answer is again in 2's complement. You can cross check also. If you do a 2's complement of this will come out to be 19, and if you do a 2's complement of this will come out to be 7. So this is addition. So let us Now take one consideration here, that in addition, if both numbers are of different signs, one number is negative and another is positive, and overflow doesn't occur or it doesn't carry sense, because if two numbers are to be added and one is positive, one is negative, so the answer obviously will be a lesser value, so there won't be a overflow, or that overflow doesn't make sense. But if both the numbers are positive or both the numbers are negative, if both the numbers in addition are positive, that means the answer will be greater than both. If both are negative, again it will be its magnitude will be larger. So there is a possibility that in this case there will be an overflow. Fine. So how to know that there is an overflow? How will the computer come to know that there is an overflow in addition? There is a simple method, that what to do, you do an XOR of the two carries. If the XOR is 1, overflow has occurred. If the XOR is 0, overflow has not occurred. What are those two carries? Those two carries are carry into the sign bit position, and the second is carry out of the sign bit position. What does that mean? For example, here is a number. So if you look keenly on this, this is a 8-digit representation. 1, 2, 3, 4, 5, 6, 7. These 7 bits represent the magnitude. This represents the sign. So this is the carry. If there is a carry into this position, this we called sign into the carry position. And if there is an extra carry that goes out at the 9th position, that we call as a carry out of the sign bit position. So if the answer is 9-bit, 8th bit represents the sign, one carry, and the 9th bit represents another carry. So we have to see what are those carries. Just do an XOR. That is why it is written carries here. Two types of will be one. What is the sign bit, and if there is a 9th bit upon adding, so that is here. So for making you understand, let us take this example here. So we have two numbers, plus 70 and plus 80. So 70 is this, magnitude of 70 is this, plus is represented by 0, and 80 is this magnitude, and plus is represented by this 0. Now let us do a simple addition of these two. When we add these two numbers, we get this thing. We get 8-bit answer. So there, this is good. Then we get a carry which goes into the sign bit position, and there is no 9th bit. So that means the 9th bit is 0, and this carry bit is this, which goes into the sign bit is 1. Now we have to do a XOR of these two. We know very well that if it is the numbers are different, if it is 0 1 or 1 0, the XOR comes out to be 1. So here the XOR will be 1. This 1 will imply that the answer is incorrect. This is an invalid answer. Why? Because the computer here can store only numbers up to 1 to 7, because the magnitude that can be stored in a register is only 7 bits. If you look here, the registers which this computer is using, it consists of 7-bit magnitude and 1-bit sign. Since the magnitude is only 7 bits, So the maximum number that can be stored in 7 bits will be 127. But when we add these two, the answer will be 150. So that means 150 magnitude cannot be stored in this computer, a computer which has this 7-bit magnitude register. So this is an invalid answer. How will the computer know that this is an invalid answer? By doing an XOR between these two. Then this XORing has to be done only in that case where the signs are same. It is plus, it is plus, it is minus, it is minus. Otherwise, there is no issue. Let us take this example. We have to do an addition of minus 70 and minus 80. That if we do an addition here, again there will be a problem. If we do an addition of these two, we get 1011011010. So there is a 1 in the 9th bit position and a 0 here. So again the XOR is 1. That means this answer is not valid. This number is not 150. It cannot be stored. We do a subtraction of two numbers. There can be 4 cases. Either both numbers will be positive, or first number will be positive, second will be negative, or first will be negative, second will be positive, or both will be negative. So these are numbers, and this is the operation to be performed. We have to do subtraction. So in this thing, the computer does not perform any subtraction. It converts the subtraction into addition. So it converts the subtraction into addition. How does it do that? It applies this minus on this. So on this thing, we apply this minus. So this becomes, this minus is applied here, this becomes minus b. So this becomes plus. So every operation, every minus operation is converted to plus operation accordingly. This minus is taken here, so it becomes plus, and this. So what the computer is doing, it will convert every subtraction operation into a addition operation. Okay, let us take examples for each. Let us take an example for this case. So first we have minus 6 is one number and minus 13 is another number, and there is a subtraction in between. So minus 6 in 2's complement is this, minus 13 is 2's complement is this, and in the center there is a minus. Now since it will convert this minus to plus, so obviously it will apply this minus on this, and negative of this number will be 2's complement of this, because when we negate a number, it becomes the 2's complement thing. So this minus is put on this and it becomes 2's complement of this number. So this number 2's complement is written here, and this negative goes off and a addition comes here. So in this way we have converted a subtraction operation into an addition operation. So adding is very easy for the ALU, and it will add these two numbers. Both are 8 bits, and answer is 9 bit. 9th bit is discarded, and the answer is just 8 bits. If we see what is it, it is plus and 7. Obviously the answer will be plus 7 here. You cross check. Let us take another example where both numbers are positive. So we have to subtract two positive numbers. So plus 6 is represented by this and plus 13 by this. Since there is a subtraction here, we will convert this plus 13 to its 2's complement, which become 9 minus 13. So this plus 13 converted to minus 13 in 2's complement actually will be this thing. So this minus will be converted to plus, and let us do the addition of these two things, which comes out to be this. And what is this? This is 7 minus 7 represented in 2's complement. Third example, one number is positive, another is negative. Again, plus 6 is here, minus 13 is here, and difference is to be done. We will apply this minus on this. This will become 2's complement. And here, minus converts to plus, and do a plus, and we get plus, and these 7 bits represent 19. Then fourth case, first number is negative, second is positive. So minus 6 is here in 2's complement, plus 13 is here, and minus is here. So this minus we will apply on this and take 2's complement of this, which comes out to be this. So since this is plus 13 and this will become minus 13 here. So this is 2's complement, and this negative will become positive. And just add these two, we will get a 9-bit answer. Discarding and carry, we get this thing, 8-bit answer. So this one tells us that it is a negative number. Since it is a negative number, that automatically means this answer is in 2's complement. So what is this? We can convert it and check. It is minus 19. So this implies minus, and we can take a 2's complement of this number, which comes out to be 19. And we can cross check that minus 19. If we do minus 6 minus plus 13, this will be minus 19. Okay, let us see the hardware implementation for this thing. So hardware implementation for this 2's complement addition and subtraction will be very simple. We will have one register in which one number will be stored, another register in which the second number will be stored. There will be an adder, parallel adder, used for addition. And if I have to do subtraction, I also need a complementer because I have to do a 2's complement. And a flip-flop for storing the overflow if there is any. So the hardware is very simple for 2's complement addition and subtraction. And the flow chart is also very simple. For add, you just put the first number, which we call as augend, in AC, this register, and the second number, which we call as addend, we put it in BR in this register. Then we directly add those two. Here is an adder, it will add this and this, and will produce an answer that will be stored in AC. And if there is an overflow, that will go to V. And similarly, if there is a subtraction, the first number, which we call it minend, is stored in AC, second is stored in BC, subtrahend. And since we have to do a subtraction operation, subtraction means first number plus 2's complement of second number. So this is subtraction operation. So this will be answer will be stored in AC. If there is an overflow, that will be in V. And